Hi, welcome to the first lesson in Unit 3, Rules of Derivatives. So, our first lesson is looking at a shortcut to what we already know. I described derivatives to you all as a slope of the tangent line, and this lesson is going to help solidify that. But we're also going to have a more pattern-based way to use derivatives. And in math we like to use patterns, so that's what we've found with derivatives. And to start off with, we're going to look at these three functions here on the left, and I've already graphed them, so you'll need to as well, so you might want to pause. But for these three graphs, we are going to look at the slope of the tangent lines you can observe. So we might have to draw some tangent lines on our graphs. Let's see, I'm going to use a light purple. So if we're reading this chart, it's already filled out, but if we're reading this chart, then the x values are static, and it's the slopes that change. We're not given the slopes of the original of f of x because the slope is just 2 for this first graph. The slope is just 2. But then if we look at the slope of the tangent line for g of x at, let's say, x equals -2, so if we look at this column and this row, we end up with a slope of -4 when x equals -2 on g of x. I would look at -2 and plot a tangent line. So over here I've drawn in light purple a negative slope of 4, a tangent line at x equals -2. And we could go around the entire quadratic and follow along what this chart is saying. At -1 we'd have a slope of -2, and at 0 we have 0, and so on. So you all could draw these tangent lines as well. You don't need to, but I'm just showing you how to read this chart here. So if we were to look at the pattern in this table, you might notice some similarities between the columns. For example, the y values of the original of the 2x are the same as the y values, or the same as the slope values for g of x. And likewise, the y values of g of x are the same as the slope values of h of x. So clearly there's some relationship happening between all of these graphs. Now, if we look at this visually, the slope values, these purple slope values, so at 0 we have a slope of 0. On the y values of f of x, there's a y value of 0. At x equals 1, so you can see how they line up. At x equals 1, the slope of the tangent line on g of x has the same y value on f of x. And same thing for -1, and that would be the same for every point on the graph. So clearly, f of x is representing the slope of the tangent line to g of x. And we could say similar things about h of x and g of x. If we were to look at the slope at 1, what's the tangent line slope at 1? I can sketch what that line would look like, that slope would look like. And we're told that the slope at 1 is is 1. We're told that the slope is 1, so maybe my line is a bit off. Go. We're told that the slope is 1, and the y value on g of x is 1. So the pattern we're getting is the slope of the cubic function is the y value of the quadratic, the g of x function. And the y value of the linear function is the slope of the quadratic function. So these varying degrees are making a pattern. So generally the greater degree function has a slope that can be represented by a function with one less degree. With one less degree, and that can be observed here. Now, the derivative is something we've discussed a lot before, the slope of the tangent line for the function. So a derivative is the slope of the tangent line for a function, for a given function. And we have used the difference quotient to describe this. So f prime of x is going to represent our derivative. And if we take we used to use h, I'm going to use delta x. That still means the same thing because h still represented the change in the x values between 2 points. So as that number gets closer to 0, we look at the slope of the function as delta x gets smaller. And we say that that difference quotient and the limit of that is the derivative. Now there's a few different ways to represent the derivative, but here we're going to use this thing called the derivative operator on any function f of x. So this is our derivative operator. It's saying you are using the derivative operation to find the slope of the tangent line. So we're finding the slope of the tangent line with that derivative operation. In our example, the linear function is the derivative of the quadratic, because the linear represents the slope of the quadratic function, and then the quadratic is the derivative of the cubic function. Now my question to you is, what's the derivative of the linear function y equals 2x? Well, we noticed the pattern, but we don't really have the pattern yet because I haven't told you. So maybe just using the definition of what a derivative is, what is the derivative of y equals 2x? Well, y equals 2x is a line. So how do we represent in general the slope of the tangent line to y equals 2x? So all this says is y prime, that's what a variable looks like after you've taken the derivative of it. That's what y looks like after you've taken the derivative of it. X, because this is with respect to x, will reduce in power, and you'll see this pattern later. But y prime, so on the highlighter, is equal to 2. So what's the slope of the tangent line to y equals 2x? It's just 2, because that's the slope of the line. That's the slope of 2x. So this says the slope of the tangent line to y equals 2x is 2. That's all that says. So what's the derivative of the derivative to a linear function? First of all, could you write that? So could you write that with derivative operations? I think we can. We have these brackets and we're kind of nesting them together. Let's just use the same linear function. Well, we know that the derivative of 2x is equal to 2. So I just did this inside piece. With these compositions, remember you can work inside out. So what's the derivative of a function that is just equal to 2? And if you want me to be a little bit more formal, that might help. What's the derivative of a function where y is equal to 2? Well, that's a horizontal line. Y equals 2 is a horizontal line. So our answer is just 0 because y is just a horizontal line at 2. So we found 2 layers of slope. Alright, so at this point I'm going to give you all a little break. You all can go watch the next video. It's going to be a little bit of application and then we'll look at some rules. Alright, so here we are, second part of the video. We're looking at this graph that represents the position of an object and its y values are listed there for us. And based on what we can drum up about the tangent lines, we're going to look at the equation of the derivative. So if we look at what's happening at 0, 0, what is the slope of this graph at 0, 0? Well, we can't figure it out because it is an endpoint and we do not have a slope to reference. So we can't draw a tangent line there. And if you remember from physics, or maybe you're just now hearing this, but velocity is the derivative of position, but it also is found by looking at the slope of position. So if we can just find the slope of the position, then we can find the velocity. So here already is an application. So if we look at 1, we know we have a point and a slope to reference at x equals 1. So at 1, 2.5. If we were to sketch a tangent line to that point on our graph, then that tangent line looks like it has a slope of about 2. Go up 1 over 1/2, it looks like, so that makes sense. And if we sketch a slope at 2, 4, that one looks like it has a slope of 1. At 3, 4.5, the vertex, we know what that is. That's a slope of 0. At 4, 4, we have a slope of -1. So, and then it looks like we could repeat the same value for 2, but we're going to stop there. So here we have our tangent line slopes, and they're listed in the table. Now, a possible equation of v of x could be found if we could just graph these x values and the y values that we were given. So instead of using the same y values over again, we don't want to draw the same graph. We're going to use the slope values as our y values. So the outputs are going to be slope. So that means we're going to find a derivative equation because the outputs of a derivative are slope. So for 0, we don't have anything. So I'm just going to leave an open circle if I can find a good place to put it. But at 1, 2, that's where I'll draw my first point. And then at 2, 1, 3, 0. Okay, we get the pattern. Open circle there at 3. All right, cool. So this is the slope in the open circle down here. This is the slope equation. So the possible equation for v of x, I think we really don't need this possible. We can kind of tell what it is because it's a pretty clear representation. It's going to be negative x plus 3, y-intercept at 3, and then a negative 1 slope. So this is our slope equation, and remember, derivatives mean the slope of the tangent line. So we have found the velocity equation. We could tell whatever velocity we want from this graph. Now, making sense of the equations, there has to be a pattern between the derivative and the function it came from. And we actually already observed this in the last video. So here I've got the functions from those first three. And this first row is the original function we start with, and then below that is the derivative. And that's represented by this little tilde between the f and the parentheses x. So the derivatives are all a degree less than the function itself. So second degree, first degree, 0th degree for g prime of x, third degree, and second degree. But what's also happened is whatever degree you begin with, so here it's 2, that gets multiplied to the coefficient in front of that function's, that coefficient in front of that variable. So I get 1 times 2, that gives me 2x. I get 1 times 2, but then my degree goes down, so it's 1 minus 1, that's 0. So I get 1 times 2, that's just 2. And now for the third and final example here, if we have a third degree with a coefficient of 1/3, we would multiply 3 times 1/3, that would be 1, and then we reduce the power of 3 by 1, and we get 1x squared as our answer. So there's a clear pattern here, and these patterns can be observed in these rules. There's 5 rules that we'll be talking about as we go through this lesson, and I want to work with them in a worksheet that we will also continue in class. And we'll only do these first 3, and then we'll work with 4 and 5 in class. To wrap up this video, we need to do some practice problems before I just set you all off on this assignment. So for these derivatives, you can see the page I got this from has a nice little explanation at the top, but it gives the rules and then some examples in context. The last example here is the derivative of just a number. 1 over pi cubed, that's just a number. And what this first rule is saying, the derivative of a constant, is that the derivative of any constant is 0 if that constant c is a real number. So the derivative of 1 over pi cubed is equal to 0. And you can extrapolate that to the rest of those answers. Number 2 gives an example of the single variable rule. So if you're taking the derivative with respect to x of x, then that answer is 1. Likewise, if you're taking the derivative of t with respect to t, of s of t with respect to t, then that answer is also 1. The power rule is the most memorable of all the rules because it has this nice little pattern that we discussed in our notes. For b, if we are finding the derivative of b, we need to have what we're taking the derivative of in this nice format. x to the n. I'm going to say we need it in the form ax to the b in order to use the power rule. Now, there's no a here, there's no coefficient, but you'll see that later on as you continue on in this practice worksheet. So the rule is we multiply our degree b, or n here, by the coefficient already there, so our coefficient is 1, and then we reduce the power of our degree by 1. So f prime of x is equal to 6x to the 5th. Notice I didn't put the derivative operator around x to the 6th, I just skipped right to it. The derivative operator is helpful when we do more complicated derivatives, but for these, the derivative can just be noted with f prime of x, and I can use the power rule to show that. Now for d, this is not really nice because it's got a radical, and that radical does not look like the form we discussed, y equals a times x to the b. So we have to see the power. We're going to rewrite this one so that we can see the power. And it is a fraction, but we can subtract 1 from fractions, so it's a lot easier to do. So y prime is going to equal 1/2, so we multiply 1/2 by 1, and then we subtract 1 from 1/2, and that's negative 1/2. So this is our final answer here for D. Now, this is a separate example because we like to leave positive exponents in our answers. And what you also notice is we didn't do that for D. However, to rewrite this one, we'd have to move x to the denominator with a 1/2 power, and that's also not very helpful. So actually, this is our best form when we were working with this this power rule. So if we look at G, we want to rewrite this one to be t to the negative 1/3. Right? So if we look at F, if this is actually x to the negative 1/3 because, sorry, to the negative 3, because 3 is our power and it's in the denominator, then we can just rewrite it as x to the negative 1/3. If t is in our denominator and we have a radical, then that radical becomes a fractional exponent, but it has to become a negative fractional exponent in the numerator. So we have used those rules that we've learned from exponents in other classes. And now we can actually take the derivative of this, t to the negative 1/3. And the derivative is actually the easiest part. Rewriting is going to be the part where we struggle some because those pesky algebra rules. There we go. Multiplied negative 1/3 by 1, and then reduce the power, that's a negative 4, of negative 1/3 by 1. So there you have it. Good luck on the rest of this worksheet. We'll talk about it in class.